Good morning. This is John Pendleton, your trainer today, and we're going to cover some superheat and subcooling calculations today and kind of what they mean. We'll get started here in just a couple minutes, maybe 2 minutes after 9 o'clock. So just a couple more minutes. Thank you. All right, let's go ahead and get started again. My name is John Pendleton. I'm your trainer today. If you have any questions, you can go to your little toolbar there on the GoToWebinar panel, and you can raise your hand. You can ask a question. When I see it, I'll try to get to a stopping point and answer those questions for you, or you can wait till the end and ask questions. This webinar is recorded, and it will be uploaded to our YouTube channel. All of our webinars are recorded, and you can go and watch those at a later date if you prefer. If you would like to, you can see some of our past webinars. And our YouTube channel is Enertech University. So you can look that up on YouTube, and you can subscribe, and it'll notify you that we've got videos uploaded there. If you have any training requests, maybe these trainings don't really work out for you or for your company, and you would like some training, you can contact me. There is my email address. It's john.pendleton@enertechgo.com, or you can call me at 618-690-3275. That's my desk phone. If I don't answer, I'm either on a site visit or in a training or obviously away from my desk. You can also talk to technical support, which is a 618-664-5860. I do work back in technical support as well, and that's a direct line there's 4 or 5 of us back in tech support. So the 618-664-5860 will ring to all of us. So the first available technician will grab that. So we're going to cover basically the pressure temperature relationship, the thermal expansion device, or the TXV, the refrigerant charge, and then how to take the measurements, the superheat and subcooling, and then once you get those readings, what those mean. Basically, all of our systems at this point, we're using 410A. At some point, I think we are going to switch refrigerants again. I'm not really sure what they've decided on yet, but we're going to be going away from the 410, I would imagine, in the next 5 years or so. The key to that refrigerant, it'll boil at a very low temperature. And once we boil, we can add heat to the system, and we can go down to about 20, 25 degrees, entering source water temperature, where we can still extract heat from that water. This is a pressure temperature chart. I'm sure if you work in the field, you're pretty familiar with these. You may have one in your front pocket right now. But we'll have to use, this is the pressure temperature relationship chart for the R410A. Basically, what we're looking at, when we change phases in the refrigerant, that's where we're going to be either absorbing or releasing energy. So obviously, different refrigerants will evaporate or condense at different temperatures when under different pressures. Before we're changing of the state, it would be considered a subcooled liquid here in this picture here. And then after the change of state, which is right here at the boiling point, would be considered a superheated vapor. When we raise 1 pound of water 1 degree, when we go from 209 to 210, we've got about 1 BTU that's either being released or absorbed there. Same thing past the boiling point. When we're at the change of state, so right there at that 212 degrees where we're boiling, that's where we're really going to be releasing a lot more of the BTUs. So that's the point we're trying to get to so we can transfer the heat, is that change of state. We want to make sure we've got plenty of superheat and subcooling. The subcooling protects the compressor, or the superheat protects the compressor. Make sure all the liquid is boiled out of the refrigerant before it gets back to the compressor. So we'll look at a few types of refrigerant circuits here. Maybe, there we go. This is a water-to-water refrigerant circuit. So in this circuit, there's not, I mean, when you walk up to a geothermal unit, you might be a little bit, unfamiliar with a water-to-water refrigerant circuit. Basically, we have 2 heat exchangers, which is the same as any air conditioner or heat pump. It's just the type of heat exchanger we're using to transfer heat. So in a water-to-water unit, we're using a water coil on the source side. So we've got a ground loop, and then we've got refrigerant in these orange lines in this picture. And the water lines will come in the ends of this source heat exchanger and transfer heat there. Now, we've also got a compressor, a reversing valve, a TXV, and a filter dryer. And then on the load, this is a water-to-water unit. So on the load, we also have another water heat exchanger as well. A split system or a package unit are really very similar to a water-to-water unit. The only thing different is now we've got an air coil on the load side instead of a water heat exchanger. And on a split unit, we do have 2 TXVs. So we've got a cooling TXV at the air handler, and we've got a heating TXV in the compressor section. So depending on what mode you're in is going to depend on where you have to check your superheat and your subcooling readings. The packaged unit only has 1 TXV, and it's a biflow expansion valve, so it works in both directions. In the same way with this combination unit, it uses 1 TXV. It's a biflow TXV, it'll throttle in both directions. The combo unit is very similar to a packaged water to air unit, except it's also a water to water unit. I'm not going to get real in depth with this today. I don't really want to confuse you, but you can see we've got a load heat exchanger, a load air coil, a source heat exchanger, reversing valve, filter dryer, TXV. But in this unit here, we actually have a 3-way valve and a directional valve, and these are energized when we're in load water heating mode. So we bypass the air coil. When the air coil calls, then we bypass the load heat exchanger. But know that if it's a packaged unit, water to water unit, or a combination unit, you have 1 expansion valve in it. And then on a split unit, you will have 2. So In a geothermal heat pump system, we must use an expansion valve. We can't use the cap tube because of the wide range of temperatures that we have going through that system, through that loop. You know, we're ranging anywhere from 25 to 110 entering water temperature, depending on what mode we're in. So in order to adjust for those water temperatures, a cap tube can't do that, or a fixed orifice piston. So we've got to use the expansion valve. Some of our variable speed water to waters or variable speed units, they'll actually use an electronic expansion valve, but the majority of our units will use the thermal expansion valve. Obviously, the expansion valve is there to adjust the charge to maintain superheat based on the entering water temperature, and it protects the compressor. Stops that liquid from getting back to the compressor. Compressors don't like to pump liquid. It doesn't compress. Obviously, the cap tube doesn't have the ability to adjust the charge, therefore it has a smaller entering water temperatures. Again, we're operating anywhere from 25 to 110 degrees, depending on the season. The only way to properly charge an Enertech geothermal system is by superheat and subcooling. Now, that being said, we do have refrigerant charge amounts listed on the unit itself. So you can always weigh the charge in if you know that there's none in the system. But if you're checking a refrigerant charge, then you'll check it with superheat and subcooling. And we'll get to that here in just a few minutes. I want to show you a little bit about the expansion valve here and what goes on with the valve. These get a lot of negative comments because they tend to stick. And there's nothing really in this valve to really break, other than the bulb might lose pressure. Maybe it rubbed on a refrigerant line, rubbed a hole in it, and the bulb pressure pushes down on the piston, opening the valve up more. The spring pressure pushes the valve up, or the piston up, and closes the valve off. So the majority of the time, I would say 99% of the time, the valve sticks closed because the bulb loses pressure, or something along that line, but the spring has so much force that it'll slam that valve shut. Now we also have evaporator pressure, which is our equalizer tube pressure, and that pressure is to keep this piston equalized so that it can move up and down. So if you ever have a TXV that fails in the field, more than likely this piston right here in the middle has gotten some junk on it, and it's stuck somewhere midway. You can actually if you remove the refrigerant from this system, you can remove the body of the valve. You can pull this piston out of the bottom, and you can take a look at it, and it's kind of tapered. And a lot of times it'll have some black sludge on that tapered portion, and that's what's making it stick, because the passageway through here is so small. A lot of times you can clean it up, put it back in, pull a vacuum, and it'll work just fine. So, sorry about that. Getting a little happy fingers there. So a TXV in heating mode, this is your sensing bulb here. As the bulb warms up, it pushes on the diaphragm, which in turn pushes that piston down, allowing more refrigerant to flow through. In cooling mode, same thing. The bulb doesn't change where it's located. The bulb for the expansion valve is located about 6 to 12 inches off of where the bulb is mounted, or of the compressor itself. And then we would normally take our superheat reading pretty close to where that bulb is located, because that's what the valve is trying to do. It's trying to maintain superheat, somewhere between 10 degrees or so. So when we check superheat, we're just going to find that bulb location, remove some of the insulation. That's where we're going to check our superheat. But the valve doesn't work any different in heating than it does in cooling. It's still sensing suction line temperature and throttles the valve accordingly. Now the refrigerant path goes in the opposite direction, but it still throttles the same. So basically an increase in suction line temperature increases the bulb pressure, thus opening the valve to allow more refrigerant to flow. As the evaporator pressure increases, then it'll start to close off that valve. Obviously, with a cap tube or a piston, or a fixed orifice, you've got to have a higher accuracy of refrigerant charge. With a TXV, we can overcharge the system, and it's not really as big of a deal because it'll just store that refrigerant in the condenser. Now, we don't want it to run with excessive high amounts of or overly charged. We can run into high amp draws and we can actually get into a high pressure situation. I actually had one last week that they had a split unit and it was overcharged by 5 pounds, and it was it'd run for a little while, then it'd start building that discharge pressure and it would go out on high pressure. Basically, the easiest way to diagnose a TXV is to remove the bulb, and you can warm it up with the compressor that's sitting right there, or you can put it in your hand and warm it up, and then get a glass of ice water, and you can cool it down and watch for your suction pressure variation. It should move about 5 to 10 psi, and when you're in first stage on a compressor, you're going to be running higher pressures than what you are in second stage, just as a side note. So I would recommend putting it in the second stage when you're doing these checks, and then look for your suction pressure variation. Superheat and subcooling will tell you as well, and we'll get into that here in just a second. So superheat, it's defined as the number of degrees above the saturation temperature of the refrigerant. Remember that chart? We showed the 209, 210, 211, and so on in the boiling point. That boiling point, we're looking at the number of degrees above that saturation temperature. So saturation temperature boiling is 212. So how many degrees above that 212 are we? So an example, if the temperature of the refrigerant is 40 degrees at 100 psi, and if the saturation temperature is 32, then we just do the math on that, and that would be 8 degrees of superheat. Subcooling is defined as a number of degrees below the saturation temperature of the refrigerant. So if the temperature of the refrigerant is 28 at 100 psi, the saturation temperature is 32, then again, we just do the math on that, and that tells us we have 4 degrees of subcooling. Again, that picture with the jugs of water, subcooling is below that boiling point in that picture. So if we look at a correctly charged expansion valve, we can kind of use a correlation to, okay, this is a reservoir or a dam here, and then you've got your outlet. It's your evaporator, low pressure coming out, and that's your expansion device, is basically the dam. So we're kind of referencing, kind of comparing the two together, so you can have kind of a little picture of what's going on with the TXV. So the expansion device, or the outlet of the dam, you know, it's only going to allow as much water as it wants to maintain. So it's going to hold all the excess back here in the reservoir. And the reservoir in our refrigerant system is the condenser, or the high pressure coil. So for a correctly charged system, the expansion device, or the TXV, it's going to adjust and it's going to maintain your proper superheat. You know, in a perfect world, it'll sit there somewhere around 10 degrees or so on your superheat. Here are some temperatures and things that you're likely to see, pressures on a normally charged system. So on a normally charged system, we're going to have somewhere around 6 to 8 degrees of water temperature difference. Usually our discharge on a compressor, somewhere between 300 and 350 psi, obviously depending on your water temperatures. And obviously your suction line is going to be a cold line. Here we're showing we got a suction temp of 29. We've got a pressure of 76. We look at our pressure temperature chart, and that tells us 76 equals 19 degrees. And then we just do the math. So that would tell us we had 10 degrees of superheat. And then subcooling, we're going to check it on the warm side of the TXV. So if you have a packaged unit, when we check subcooling, you can grab this line, and in cooling, the liquid line is going to be in between in this diagram, the filter dryer and the TXV. So that's where you're going to check your subcooling and cooling. And subcooling and heating is going to be between your load heat exchanger and your expansion valve. Easiest way to tell, guys, is the warm side of the TXV. There's a lot going on in that little box. If you've ever looked into the bottom of one of our packaged units, there's a lot of refrigerant piping and stuff going on, so it's kind of hard to see in there. It's kind of hard to trace around, see what the inlet and outlet is. So the easiest way to know for sure is the warm side of the TXV. So here we're in heating mode. We've got a liquid line temperature of 90 and a discharge pressure of 300. That 300 converts to 96 degrees. So we take 96 minus 90, that gives us 6 degrees of subcooling. We do have charts in our IOM that will tell you on the different tonnages what superheat and subcooling we're looking at when we have 30 degree entering water temperature or 50 degree entering water temperature. So if you've got access to the IOMs, always check those out and look. If you don't have one, you can always call us in tech support. If you don't have cell phone service or something, a good rule of thumb for all of our units is somewhere around 10 degrees superheat, 10 degrees subcooling. So if you can get it within 3 or 4 degrees of 10 on those, then we're looking pretty good. And to be honest, that's a good rule of thumb in our industry, somewhere around 10 degrees superheat, 10 degrees subcooling. So an undercharged system, your condenser or your reservoir in this example, the level is going to be low. So even if this expansion valve or the outlet of the dam opens up all the way, there's not enough refrigerant flow. What will happen is you'll have high superheat and you'll have low subcooling. Here's an example of that. So we've got, again, we'll check our discharge pressure, which is 260 psi, and it'll convert to 87. Then we're in heating mode. So again, warm side of the TXV. We want to go to the warm side and check that temperature. Here it's 87 degrees. So we have 0 subcooling. Then we'll check our superheat. And to be honest, it doesn't really matter to me if we check superheat or subcooling first. It doesn't really matter. We're going to check both of them anyway. So whichever you feel like checking first is fine with me. The superheat, we had a suction line pressure of 68. So if we look at the pressure temperature chart, we'll cover that here in just a few minutes when we go through some practice exercises together. But that tells us that's 14 degrees. When we actually check that line temperature, it's 29. So 15 degrees superheat, 10 degrees subcooling. So if we go by my rule of 10 and 10, our superheat would be a little bit high and our subcooling is definitely low. So that would tell us that we're undercharged. In our IOMs, we will list these charts here that will tell you if it's undercharged and you're in heating mode, what will some of the symptoms be? So low discharge, low suction, high superheat, low subcooling, low air temperature difference, low water temperature difference, and your amp draw will be low. And we have these for overcharged, undercharged, no load water flow, no airflow, no source water flow, a restricted TXV. So we'll kind of help you in the troubleshooting section of our IOMs. So always check those troubleshooting sections, and we'll try to give you a little bit of direction on what might be going on with the system. In an undercharged system, you're going to have low subcooling. Your pressures in your compressor amps are going to be low because you have lower vapor pressure, and it creates less load on the compressor. You actually be pulling less amps. Undercharged and cooling, not really a whole lot has changed. Your evaporator will be starved of refrigerant, and the liquid level before the TXV is going to be low. It's going to result in high superheat and low subcooling. Normally, it will not freeze up the entire coil either. You'll have some ribbons of frost maybe. But if you see a big block of ice that's on your air coil, that's normally due to a lack of airflow. So if it's a big ball of ice, you got to thaw it out and check your air filter. If you just see a little bit of ribbons of frost, maybe some on the U-bends, that's more indicative of an undercharged system. Sometimes you can also get a little bit of frosting or condensation on your expansion valve as well. Overcharged system. For an overcharged system, the condenser or the reservoir, it's going to be high, and the expansion valve is going to close off. So it's going to maintain proper superheat, but you will have high subcooling. So normal superheat due to the expansion valve. So it's really hard to flood with an expansion valve, unless you overcharge the system by about 5 pounds, and then you're going to have some problems. The TXV basically is going to hold back the refrigerant, and it's going to hold it in your condenser, which in heating mode would be your load side. So here we've got a 16-degree subcooling, 10 degrees superheat. Again, if you remember 10 and 10, that would tell us superheat looks good, but our subcooling is high. Normally, when you see your subcooling, you're going to see more like 35 degrees, and then your superheat maybe 10, 12 degrees. Some of the systems of an overcharged system, high discharge pressure for sure. And a lot of times what it'll do is your suction will stay pretty consistent. It may raise a little bit, but your discharge will slowly start to raise. Sometimes it'll shoot up fairly quickly, and sometimes you can go out on high pressure. So again, your suction pressure could be normal, could be a little bit high. It won't be extremely high, but it'll be a little bit high. Superheat normal, subcooling high. You have a high air temperature difference, and normal on your source side. And your compressor amps will be high as well. Basically, your high pressure is building up on the discharge, and it increases our compression ratio, which is our discharge divided by our suction pressure. So the farther those get apart, the higher your compression ratio and the harder it is on your compressor. Your compressor is going to run real hot. It could go out internal overload before it goes out on high pressure. It's really just kind of depending on how long it's been running with that excess refrigerant. The superheat, again, it's going to remain constant, but you will have high discharge pressures, and they will slowly climb. I wanted to mention this because I mean I do it all the time, and I know guys in the field do it as well. I mean I was in the field for over 25 years, so we used to charge systems with a fixed orifice when we just say, oh well, it's beer can cold, we're good to go. Charge is good to go. But here's some temperatures if you're just interested to know. At 140 degrees, anything above that, and you can't leave your hand on the line for very long. So if you touch the top of that compressor, it's real hot, can't leave your hand on there. That's because it's probably over 140 degrees. If you ever worked in a system and you got it running, you're reaching around in there and touch your forearm to that top of that compressor in the middle of the summer, it's probably going to be pretty hot. So that's above 140 degrees. At 85, that's a neutral temperature. Your external body temperature is about 85 degrees. So less than 85, it's going to feel, maybe lukewarm or warm, or excuse me, anything 85 and above, and 85 and below will feel kind of neutral to cool. You can also, the minimum amount of temperature difference you can feel with your hands is about 5 degrees. So if you ever touch a desuperheater line and it feels the same temperature, there's normally only on a desuperheater about 3 to 5 degree temperature difference. So you may not be able to feel it. But these are just some of the temperatures, because I know you guys are going to grab lines and touch them and see their temperatures, see if they've got heat in them or if they're cool. And so there's a little bit of information on that. Going through the system, here is a desuperheater right there in the middle, and that's got less than a 5 degree temperature difference. It's really going to depend on your discharge pressure. This pressure is temperature. The higher your discharge pressure, the higher the water or higher the gas that's flowing through this is, the more temperature difference you're going to get. It's also going to depend on your water flow. How long are you running this line? It's a real short line. You probably got a lot of flow. If it's 50, 60 feet, you may not have quite as much flow, so you could have a higher temperature difference. Depending on what mode you're in, the expansion valve, if you're in cooling mode, you're going to notice a great big difference in between the inlet and the outlet of the valve. Somewhere between 85 and 110 is going to be your warm side, and the cold side is going to be, 60, 70 degrees. Your suction line, where your bulb is located, it's usually 30 to 50 degrees, so definitely cool. Your discharge, somewhere between 120 and 180 degrees, so it's going to be hot. On your water lines, on an open loop, where we're moving less flow, you're going to have 8 to 16 degree temperature difference on the water in heating, and you could have 18 to 24 in cooling. And on a closed loop, you can normally cut that in half because we're moving twice the amount of flow. So 4 to 8 in heating and 9 to 12 in cooling on a closed loop. Open loops, we'll use 1.5 GPM, and closed loop, we normally use 3 GPM. And so the slower you move the water, the greater the temperature difference, and vice versa. The slower you move it, the greater the temperature difference. I'm sorry, I think I messed up on that. The more flow you have, the less temperature difference. It's not in contact with the pipe as long, so it can't transfer as much heat. The top of the compressor should be hot. The bottom should be cool. If you see frosting and stuff, that's usually a sign of possible overcharged on that down here at the bottom. So an expansion valve, it feeds refrigerant based on the measured superheat or the bulb pressure. As the bulb temperature warms up, it pushes more pressure on the piston, thus opening up the valve more. It's able to handle a wide range of capacities. Again, we're ranging anywhere from 25 to 110 degrees. You can't really flood a compressor by overcharging it. You have to put quite a bit in there. That one I had last week was one of those situations. They had a lot going on there. They had actually, I think that they had probably overcharged it It went out on high pressure, and they thought it was a TXV, so they had me come out there. And it was an outdoor split, and when the high pressure went, they just shut the unit off. Well, an outdoor split has a pump on it, and when it gets below 30-degree entering water temperature, it runs that pump all the time so it doesn't freeze. Yes, you do have antifreeze in it, but only down to 15 degrees freeze protection normally. And it got pretty cold this winter, and they left it off. The pump wouldn't run, and they froze it. So I get out there. I ended up finding the leaking flow center, and got that fixed. Then went to look at it, and it was still going out on high pressure, not quite as quickly, but it was. And then we found out that they had 5 pounds of overcharged refrigerant in there. Split units are a little bit different. There is a charge amount on them, but then you have to charge for your line set. So the best way is to use superheat and subcooling on a split unit. I guess they're fairly expensive. The expensive part, I guess, is installing them. If you don't have to change your expansion valve, we definitely don't want to, because we got to break into that refrigerant circuit. So it's kind of an expensive repair, and a lot of times, again, the TXV gets blamed for things it's not. It's really its fault. All expansion valves will have a little bit of hunting in them, so you might see a little bit of jumping around on your pressures, but you shouldn't see a whole lot. And again, we're going to store that excess refrigerant in your condenser. So when we get into overcharge conditions, we're going to have high subcooling. Your superheat's going to be maintained by the valve, and you're going to have really no change in capacity, but you will have compressor high amp draws. You can actually hear that compressor once you get over about 400 PSI. You can really start to hear that compressor start to really work a lot harder, and it'll just have kind of a different sound. In an undercharged condition, we have low subcooling, high superheat, low capacity, and your compressor will be hot. Restricted or bad, it really depends where it's restricted. I have seen a few times where the valve gets stuck mid-position, and so it may work fine for a while, and then when it needs to start adjusting, that's when we run into our problem. So restricted, we're going to have high subcooling, high superheat, low capacity, and possible frost on the TXV. So let me exit out of this here real quick, and I want to get to some calculations here. Hang on 1 second for me. Oh. Okay, so we're going to go and we're going to do a couple practice exercises here, some superheat and subcooling together, just to kind of give you a little refresher of where we're checking things and what they all mean. When we're performing these readings, we do have Schrader ports on the discharge and suction lines of the compressor. If you have a packaged unit, underneath the return, there's a small door, and you can take that door off and you can access your desuperheater pump. And right next to it are your high and low service ports. And those go directly to the suction and discharge. If you have a split unit, take the top off the unit and go inside near the compressor where your high and low pressure switches are located, and you'll have service ports there as well. Now, don't put them on the king valves on the outside of the unit, as it won't read refrigerant pressures properly there. So take the top off and dive into the unit and put your refrigerant gauges on there on a split unit. Make sure your sensor location is free of any insulation or glue, and and it should be securely fastened and insulated from the ambient temperature. I like to use a little clamp temperature probe, but you can use whatever you feel comfortable using. Make sure you allow a little bit of time for that sensor to read the correct temperature of that line. Sensor location for superheat will be the same for cooling or heating, and it's usually about a foot or so off the compressor suction line. Really, you can look for the insulation that has the bulge from the bulb on the from the TXV, and you can check it right there. You got to figure that TXV is trying to maintain superheat, so wherever it's reading at is where you need to be as well. Subcooling, it's the inlet side of the expansion valve, and the easiest way to know is it's the warm side of the valve. Charge adjustments are required. You got to take refrigerant out or put refrigerant in. Put some refrigerant in, wait about 5 minutes, and let it kind of balance out a little bit, and then check your readings again. Obviously, we don't want to use this type of temperature probe on a refrigerant line. They just don't work very well. I would recommend using the clamp-on style. So in heating mode, again, I don't really necessarily care if you check superheat or subcooling first. It doesn't really matter. I think in these, we're normally going to start with our superheat. So the first thing we're going to do is remove some of that insulation on the suction line of the compressor, and put your temperature probe on there. Now you're going to check your suction pressure, and you're going to convert that to temperature. You can do that with the refrigerant gauge that's on your manifold, or you can look at your pressure temperature chart, and then we just do the math. Subtract our suction line saturation temperature from the actual line temperature, and that gives us our superheat. Cooling mode, again, it doesn't change when we're in heating or cooling. It's still a foot off the compressor, and we're converting suction pressure to saturation temperature, and then we're just doing the math on that. Subcooling, now we're in heating mode. Actually, I need to move this up. It goes on this line here. And we're going to check that temperature, and then we're going to take our discharge pressure, and we're going to convert that to temperature, and then we just do the math. And that gives us our subcooling. That's the heating mode. In cooling mode, the inlet switches sides, and so now we're on the in between our filter dryer, or I should say our source heat exchanger and our TXV, because sometimes at the factory they put this filter dryer on the other side. So we try to put it on the cooling side, so we run the unit in cooling first, so it collects that debris before it gets to the expansion valve, but I have seen them put it on the other side. So the inlet for cooling is in between your source heat exchanger and your expansion valve. So again, you're just going to measure your line temperature, check your discharge pressure, and convert that to temperature, and then do the math, and that gives us our subcooling. Superheat range is usually about 8 to 12. That's why I say the 10 number is a good number to remember. And subcooling is somewhere between 4 and 16 normally. So again, 10 falls right into the middle of that. You can always base them off of the parameters in the IOM or the EDIM, and it'll tell you, we actually have some extended data in there, and it'll tell you if your water temperature is 35 degrees and you're running 9 GPM, that you maybe should have 3.6 degrees of subcooling and 4.8 of superheat. I just kind of made those up, but you can actually really narrow it down in some of our extended data tables, but getting it pretty close is good for me. I'm not, if it says it needs to be 4.6 in the book, I don't expect you to get it exactly to that 4.6 degree mark. Plus or minus a few degrees here or there. Here's a chart that is that we will list showing some of the, in the troubleshooting section, discharge pressure, suction pressure, superheat, subcooling ranges, air and water temperature differences. Now we are using 70-degree entering air temperature and heating and 80 in cooling for this. So it could be a little bit different for you. In cooling, we're usually cooler than that on our return air temperature. Heating, that's probably pretty good, but in cooling, I would say we're probably closer to 75-degree return temperature. Really depends on the home, I guess, but we're probably a little bit lower than that. So we'll go through a few practice exercises to wrap this up here today. We're in heating mode. We're going to check subcooling first. Again, it doesn't really matter too much what you check first. If it's a packaged unit, where you're going to have to check for the line temperature at your TXV is inside the blower cabinet. So you're going to have to remove the door, put your meter on there or your temperature probe on there, and put that door back on. If you leave the door off and you're in heating mode, then you're going to go off on high pressure because we're not getting rid of that heat into the home. We're not getting airflow across the air coil if you take the door off. We have a negative pressure coil, and so, you know, air is going to take the path of least resistance to take the door off, and then we don't get airflow across the air coil. So take the door off, put your probe on there, shut the door back up. Check our discharge pressure of 330 psi. And here's where we look at our pressure temperature chart. So if we had 330, that would tell us that's 102 degrees saturation temperature. So you kind of got to write that down. And then we'll look at our line temperature. Our line temperature was 94.3. So that tells us we have 7.5 degrees of subcooling. Again, that's only part of the equation. So we'll go ahead and we'll move on to our superheat. Again, superheat is not going to change from heating to cooling. Right there where the bulb is located, measure our suction pressure of 110. And we'll look at our saturation temperature at 110 psi. So 110 is equal to 36 degrees. So we have our saturation temperature of 36. Our line temperature is 47.5. So then again, we just do the math. That gives us 11.5 degrees of superheat. So if we say, well, John said 10 and 10, we're at 7.5 and 10.5, 11.5. So that's pretty close. That's plus or minus a few degrees. So but we can actually compare it to the chart in the ION if you have it. So again, we had 30 degree or 70 degree entering water temperature. Our subcooling range, I'm gonna drop that circle down a little bit. Sometimes when I get these, I change these over to a wide screen and it messes them up. But so 7 to 12 is our superheat or our subcooling, and really 10 to 15 for our superheat. So we're within range of those. So, you know, the system, yes, is working properly. We'll look at another one here. We're in cooling. We're going to check our subcooling. So again, warm side of the TXV is going to be between our condenser and our expansion valve. Discharge pressure of 260. If we look at our pressure temperature chart, 260 is equal to 87 degrees. So we know our saturation temperature is 87. Our line temperature is 76.8. So that gives us a 10 degree of subcooling. Now we'll go ahead and we'll do our superheat. Again, 6 to 12 inches off the compressor or near the TXV sensing bulb. And then we'll look at our suction pressure. Suction pressure is 130. We'll convert that on the pressure temperature chart. So 130 is equal to 45 degrees. Our line temperature of 57.1. So we have a superheat of 12.1. We had a subcooling at 10.2. So we'll have to look in the IOM and we'll compare. It doesn't look too bad if we look at our 10 and 10, rule of thumb. But we can look in the IOM, 8 to 14 and 10 to 14. So we had, our subcooling is within range, and our superheat is within range. So yeah, it's operating properly. We will go through another one here. We're in heating mode. Discharge pressure is 335. And if we convert that, 335 is equal to 104 degrees. So we'll have to just remember that number there. Now we'll measure our liquid line temperature. Again, warm side of the TXV, and cooling, that's between your load and your TXV. So we have, once we do the math on that, we have 14.9 or roughly 15 degrees subcooling. So we'll move on to our superheat. Suction pressure is 74. Now we'll convert that to temperature. 74 is equal to about 17 degrees. Now we'll measure our line temperature at our TXV bulb location. And it's 29.4. So we do the math on that. We have 14.9 degrees of subcooling, 11.4 degrees of superheat. So compare that to the chart. We're in heating mode. Should have 6 to 12 degrees subcooling, 9 to 14 on our superheat. So subcooling, we're a little bit high on our subcooling. And our superheat is on the money. So is the unit charged properly? No. Normally, your subcooling is going to be a lot higher than this, maybe 20, 25 degrees, and your superheat would be normal. But this would show, if we look in the IOM, it would tell us if we have high subcooling and normal superheat, that more than likely we're overcharged. We'll go through one more here. Now we're in cooling mode. Discharge pressure of 310. We convert that to temperature. So 310 is 98 degrees. Measure our line temperature of 94.3. And so we have 3.7 degrees of subcooling. If you remember the 10 and 10, you're already thinking, well, that seems kind of low. But we'll go ahead and check our superheat. Pressure converted to temperature. So we have 120 psi, and that converts to 41 degrees. We measure our line temperature at 57.4. We do the math because it's 16 degrees of superheat, 16 and a half, and 3.7 of subcooling. So we refer to the IOM. Cooling mode, 90 degree entering water. We should be 8 to 14 on our subcooling and 10 to 14 on our superheat. So we have low subcooling for sure, and our superheat is high. So is the unit charged properly? No, it looks like it's undercharged. Again, this is listed in all the IOMs, so it can help you. if you're not sure what the superheat and subcooling really means when you get the numbers. So if you have, obviously, if they're both normal operation, if you have normal superheat, high subcooling, then you're going to be overcharged. High superheat, low subcooling is undercharged. High superheat and high subcooling would be restricted or stuck closed expansion valve. And if your superheat and subcooling are both low, then your TXV is stuck open. Very rarely will you see that last one there. Again, it's got that, unless something happens to that spring on the bottom of that valve. I've never seen anything happen to those springs. That spring will always slam that valve shut. So that's why it's either going to be restricted halfway or it's going to be stuck closed, more than likely. We do have a troubleshooting forum that's in all of our IOMs, and it'll help you trying to figure out where your superheat and subcooling readings should be taken. If you're not really sure, don't feel comfortable doing it, you can always fill out as many of these lines as you possibly can, and then call us in tech support, and we'll walk you through it and help you figure out what's going on. Now, don't just go up to a geothermal unit and do superheat and subcooling readings on it. These are a sealed system, and every time you put your refrigerant gauges on there, you're going to take a little bit of refrigerant out. So over time, you could become low on refrigerant. If you just want to check performance on the unit and see how it's operating, then we can check heat of extraction or heat of rejection, and that'll tell us performance. If the performance is off, then we go to the superheat and subcooling readings, but only after we decided that our heat of extraction or heat of rejection calculation is not correct. And then in order to check heat of extraction rejection, without getting into a whole nother webinar today, you're going to have pressure temperature ports in your source water, check the temperature difference. You get your GPM on your pressure difference, and you do the math on that. You can compare it to the IOM. And then if it works out, then we know that the refrigerant circuit's okay. So there's no need to put your refrigerant gauges on there if your heat of extraction or rejection work out okay. Also, don't expect the unit to operate properly if you do not have airflow or you don't have water flow. The refrigerant circuit will be all jacked up. So we've got to have airflow within specs and water flow within specs. So make sure when we do heat of extraction or rejection, that'll let us know that we've got proper water flow. Airflow is usually pretty easy to, you can tell if the fan's running or not, if it's a packaged unit. If it's a load, you have to check pressure drop on the coax, make sure you got load water flow. Also do an amp draw on the pumps, but always make sure everything in the box and outside the box are working. They're turning on and coming on before we dive into the refrigerant circuit. So again, check superheat subcooling only after we've confirmed that the heat of extraction or rejection is not operating properly. Now, if you've made a repair, you've already got your refrigerant gauges on there. So I would go ahead and, of course, check superheat and subcooling. I would also check heat of extraction or rejection, depending on what mode you're in. But always check, make sure all the components are working first. We got to make sure everything's working or turning on before we can expect anything to actually work, heat or cool properly. We do have another video on our YouTube channel. We're not going to watch it today, but it'll show you on a unit where we're actually checking, and it'll show the meters and things, and so you can actually watch that video on YouTube. Again, our YouTube channel is Enertech University. So with that, that's all I have today. Let me get to my contact info here real quick, so you can, if you need that, it'll be here for you. Bear with me. There's my email address, as well as the contact number for Enertech. That 664, actually, that 0 needs to come out of there, but 9010, that'll ring to the front desk. You can always ask Bob to transfer you back to tech support, or you can dial 618-664-5860, and that'll call directly back to tech support. It'll just be the first available tech. If you have been working with a technician and you get the group, you can ask for that technician, and if they're available, we'll transfer you over there to them. So with that, that's what we have for today. If you have any questions, feel free to ask. If you think of something afterwards, feel free to shoot me an email. If you would like a PDF of this training today, you can shoot me an email, and I'll send you a PDF copy of it as well. So, thanks for joining, and have a great week.